Hello, gentle readers. Welcome to today's episode of Moment and Motion in 3D, space and time. Moment and Motion. Today, July 22nd, 2024. From my desk with Ross Finlayson here in Seattle, Washington. A cooler afternoon as summer commences, proceeds, and consumes the world, as it were. That today, what I want to talk about in Moment in Motion is more about this idea of Zeno's swath, which is a sort of integral about all the sum of history, sum of potentials, which makes to arrive at analytical forms in the infinitary expressions for the infinitely many higher orders of acceleration, which reflects the basic proposition that 0 meters per second is infinity seconds per meter. And the slightest change with regards to a constant acceleration, or is a constant acceleration of acceleration, or a constant acceleration of acceleration, or a constant acceleration of infinitely many higher orders of acceleration, has a starting and a stopping, and that our classical laws of motion have to build to reflect this, and that our classical arguments for continuity, or Zeno's arguments, have to build and reflect this, so that it's as of a sort of what's called Zeno's swath, with regards to how it can be that it approaches from a motion to a rest as of cutting around the corner of infinitely fast to zero, and from rest to motion as from zero to infinitely fast, where that's normalized to 1. So the idea is that there's a starting and a stopping, or to keep things simple, just a proceeding from 0 to 1, and being at rest at 0 and a rest at 1. And otherwise, as with regards to being velocity 0 at 0 and velocity 1 at 1, or velocity or acceleration 0 at 0 and acceleration 1 at 1. In distance terms, for length terms, both with the same units as considered as length, yet distance as being sort of a matter of time, always. And then the velocity is always displacement over time, yet it's also the distance, as it were, with regards to things like the difference between speed and velocity. And they're not the same. Well, they are, yet, except that one kind of changes around in these various sorts of the fictitious, which is what classical mechanics and our physics offers today, as of how things are defined to be in the definitions and the terms, when really it's all quite real somehow. And so we need to figure out how to bring the infinitary expression of the infinitely many higher orders of acceleration into the well-defined and the real. So the way I was thinking about this was basically think of it as a box. And it's a particular kind of box because between 0 and 1 is from any corner to the opposite corner. So a box has got 6 sides, right, and 8 corners. And for any given corner, there's an opposite corner. Now the sides of this box are of arbitrary length. And as well, kind of the angles of the corners are arbitrary, like a rhombus or the rhomboid. Yet at the same time, there's sort of an idea that it's of the shapes that it results that via an affine transformation overall, that it can be considered a unit side length cube, or a square, or a cube. So the idea is then to figure out that from point to opposite point is the diagonal. It's called that even when it's not like when it's just splitting the angle, the diagonal of a square. And then also with regards to a box, it's kind of in the cubic. It's kind of splitting each of the 3 angles of the corners. And similarly for the higher order cubes, the tesseract, the 4-dimensional cube. What does it look like? I don't know. doesn't exist in three-dimensional space and projection. It's just arbitrarily a geometric figure with 4 dimensions. And then the side lengths are like so, and then that has opposite corners like so. And similarly, the tesseracts, and then the hypercubes. And then as with regards also to like these rows, columns, pillars, files, I rows, in the idea of taking any one of these cubes, making it into blocks, like just blocks that make a block matrix of these things, vis-a-vis the continuous from 0 to 1, from point to point. That then the idea is to consider all these different forms that paths could take that reflect, that add up to the diagonal. So it's kind of the same concept or similar as the path integral. So the path integral is a concept from quantum mechanics, because in quantum mechanics we have particle wave duality. So when a particle travels from 0 to 1 in a straight line, then as it's wave-like, then in the optical it's considered to kind of travel all the different paths around until it arrives, and then it goes on. And as about this, as we talked about here, various of these readings from Feynman's books and from our treatise on the path integral. So the idea is that it's a little complicated trying to consider every possible line that goes from point to opposite corner of this cube. And then with regards to, for any one of those that it does have a sort of reflection about it, about the main diagonal. So when we say the main diagonal, we mean from this corner to the opposite corner, whereas then there's the reverse diagonal or the opposite diagonals or the non-diagonals, which are from these other corners. So from corner to opposite corner, or T0, V0 or P0 to P1, T1 or V1 on the other side of this box, any particular contrived path has its reflection on the other side of this diagonal. And so then it gets into, when it's in higher dimensions, that does form multiples. And so there's when there become these multiple reflections, then there's this notion that adds up to also make usual models of diffraction, reflection, and refraction, making diffraction. And with regards to then all these paths through a 1 by 1 square or cube, a 1 by 1 by 1 cube, that then there are all the possible paths. And so that they add up in the average, in the weight in the middle of them, to that main diagonal. But then anything that goes from point to point will usually, by the law of averages, never be that. Yet it all adds up to being kind of average this way. So among these different kind of curves that go from point A to point B, they're considered these extreme curves, and that are kind of like, well, what about the one that just follows the sides and it just goes to the corner and then to the other side and then up, say, in these 3 dimensions, X, Y, and Z, say. And so that's a particularly contrived, sort of the longest path that's still always going in the direction of its goal. It's extreme in this sense. So the idea is that between that and the main diagonal are the gradations among those two. And so those form an infinite series of expressions. And so any path can be made as kind of like the Taylor series and Fourier series analysis, but here the Fourier-style analysis for these different functions, that the main diagonal can be added up to be of those, instead of the those being as of differences from the main diagonal. Because the main diagonal doesn't have any differences to add up to these extremes. But the extremes, their complements and differences, can divide down to it, in a sense. So this is pretty much what I've been thinking about, is how to figure out, how to make it so that the unit box has for its main diagonal, and then that living on the identity dimension, so it looks like 0, 1, and then the space around it affecting to reflect the course of all the paths that could possibly always go in the right direction, and ultimately arrive at the same place. And then that of those there will be forms, so that it becomes that the parameters of the shape and scale of these forms, distributions or forms, add up to 0, 1 for any contrived affine scaling of this box that says, okay, this distance occurred in t amount of time and x amount of length for other variables in the box, thinking inside the box. And thusly, that for any kind of action that results kind of starting and stopping, is that courtesy the symmetrical about the main diagonal, and is from the beginning and end, that those just kind of add up to be what is this Zeno's swath. Again, and then here for this talking about the extreme case, that to get into that for a minute. So the extreme case is down the sides and reaching the adjacent corners and proceeding to the opposite corner. And the reason why that is so is because there's no longer a path that it can take with regards to that being just a matter of deductive inference, that the path is the long road, or the high road and the low road, as it were, with regards to the high road, the low road, the distance, and these kinds of things. So, and now that's kind of an angular path. Then otherwise you might consider, well, eventually these paths can't just be straight or right angles. They have to have some form of curve. Here then, that gets back again to the kind of these ideas of the descriptive differential dynamics of this, the hat analysis, because this is what it ends up being, as sort of a hat analysis, that taking that corner is kind of like the sawtooth with the blunt sawtooth, or the round sawtooth, a triangular wave, so that it looks like a path between 0 and 1, and a triangular wave above and a triangular wave below, and that arbitrarily those are as reflected by as if a hyperbolic, or just like if that was the infinite quadrant shrunk to a 1 by 1 box, and then as that flattens, as that multiplies out, that just gets multiplied. It's an infinite expression, is what brings it down flat to the line again. So it's kind of the reverse of adding up trigonometric series to approximate any kind of function. It's dividing or subtracting them to result a straight line. So kind of from the little end, from the usual series being sort of the usual sorts of power series in the big end. This is how close it is to other usual styles of analysis already, to make it tractable, that there's this kind of Zeno's swath box, and what it is it's a cube, and it's got a main diagonal, and then all these sorts of paths that are most extreme have then, that it's according to an infinitary analysis, that it's and their shape parameter is the integers infinite, and then it results that when it's infinity of those functions, that it equals the flat line. It's Fourier reverse, instead of adding up periodic functions to result any particular contrived function for finding their coefficients in the finite. It's just having it that however it's possible where it ends up being the parameters like, well, how far off could you get on your way from point A to point B and still arrive? Or how extreme is the acceleration at any given point indicates how how big the parameter is of these functions that have to then divide themselves or subtract themselves back down, making this power series of a sort of negative terms adds up to 0. So that's kind of how I've been framing it. So besides then, like the plane right angle case and the sawtooth wave, then there's a couple other different main lines of approach to consider, and probably the most usual one to consider is the sigmoid line. So it starts kind of flat, and then it ramps up as high as it goes, and then it slows kind of flat. And this is the idea that kind of like the cumulative distribution over the probability distributions, and where it's like, well, from the minimum value to maximum value, it's somewhere less than that. And so it adds up, and this, for central tendency things like the normal distribution, yeah, it looks like a sigmoid. And the difference between this and the sinusoidal is that it's sort of as if it took only one period of the sinusoidal and then multiplied that by infinity, that its wavelength was infinity. But at 0, it's got its maximum gradient. So there's this sort of sigmoid, and then this reflection about it. And it's got 2 reflections at least, one from 0 to 1, the beginning to end, and one from side to side, or either x or y or z, the co-semi-dimensions of this identity dimension, the main path from 0 to 1. So the idea then that the sigmoid kind of function is the next, or it's one of at least 3 kinds of functions that add up together, that then they make an analysis together to make the terms to then to be able to say that yes, no matter any kind of other considerations with regards to any other thing in space-time, that this box models a starting and a stopping, or even also just plain old constant motion. Right. So this is trying to think inside the box. Well, to think inside the box, first we kind of need a box for it to live in, you know. And so this is kind of the idea is to kind of try and figure out this way. So the sigmoid line then is then as well for what is otherwise the contrived that would be like the constant, and whether the constant is and it depends whether this box is the box of the time dimension, the box of the velocity dimension, the box of the nth order acceleration. That no matter the order, it's kind of like it's got its own box, you know. And at the same time, that it all fits. At the end of the day, it's just as if, you know, you have a chronograph, and at any particular time you can say that yes, according to all Galilean physics and Zeno and the Mertonian school and everybody else, including your own eyes, that yes, this is well defined. The position and velocity and acceleration of any given item with respect to any given frame it lives in. That this is also going to be suitable for a relativistic setting, where the frames, spaces, and space frames of general relativity are to indicate that, yeah, this is a real box, even in the warping of space-time according to the passage of objects in space or the free rotation of objects in space. Here there's been a long discussion about the general theory of relativity, and reading from Einstein's Out of My Later Years, which really made a lot of opinion kind of finalized as the least amount of mathematical principles and physical principles and the laws according to Einstein, will result the theory of relativity, and that it's kept pretty simple, and it allows for the Galilean and the linear and the Lorentzian and the rotational as with regards to mass energy equivalency and space contraction, and these space frames and frame spaces, or the spatial and spatial, but about the spatial and the coordinates and space contraction. That warp then is just an idea of the conformal mapping that results the locally affine, and that there's still a norm everywhere to everything, that instantaneity is a thing throughout the universe we inhabit, as we're earthlings and live on Earth, fellow earthlings. So, gentle readers, that's what I've been trying to figure out, is what way to formalize matters of definition that result a diagrammatic setting that make for that. Then it's arrived at some forms then to determine the coefficients of these infinitary expressions, and they may be singly infinite or doubly infinite, or as according to the regular singular, and here the hypergeometric are also kind of defined terms. That then it arrives at something to make for a mathematical device, an apparatus, a means, to then work up numerical methods and the such like to help arrive at ways to better deconstruct the sum of histories, sum of potentials, and to have it so that change as a continuous process and an infinitary process that's formal and while non-standard yet extra standard and with real analytical character throughout is the goal. That is the goal as what to equip the principles of mechanics with the mathematics and a mathematical model so necessary to arrive at something different than what we have, only insofar as augmenting it with this fuller definition that still then just builds all that in the limits in the middle itself, Newton's force equals mass times acceleration, again, as just another straight line that results from this hat-style inverse Fourier setup. So then it results, and it's to carry on that it's just pretty much arithmetic and algebraic or geometric. It doesn't necessarily involve higher mathematics at all, except insofar as there's the unbounded to figure out. And then there are deductive results to arrive at things like the continuous drawing of a string. Kind of like if you look at a jump rope and it's spinning around, you see when it's at the top of its loop, it's perfectly curved, but at some point in time, it looks like a straight line. And as it goes around and around, if you spend a lot of time jumping rope or something like that, you know that helps to establish that matters of perspective and projection can make from the zero to infinite locally, besides just that things very far away down a long path, hallway, go to 0, point at infinity. So the projective and perspective are very relevant complementary concepts to geometry and motion, and geometry is motion, thusly, in this kind of way. So it's not so much higher mathematics, except a bit lower mathematics and a bit deeper mathematics. That these days, according to our law of large numbers, is about the highest mathematics that there is on the books in the standard linear curriculum. I have a mathematics degree. I sat enough college credits in the university to get a bachelor's degree in mathematics. But I've studied it for like 30 years on my own, out of my own interest. I don't really spend full time on it though. A moment like this is between the last talk and this one, like I had a few moments of insight. Like, oh, I was like, oh, well, the path, the Zeno swath path, has got to have like a box to live in, and it's already had the identity dimension kind of an idefix, and this hat analysis for the one corner, and then this idea of the hat analysis is kind of this inverse Fourier or divisive Fourier, subtractive Fourier sort of a thing, which is limited even much more than the Fourier is limited to a bounded interval. I mean, this is just in the box only, you know. So I'm trying to help establish that that's the kind of the bound. So I put about that much time into it between now and then, but that allows a lot of time for it to digest and subconsciously, because then in sleep, for example, the brain is free to just hammer away on these things. What if it to if, you know? What if? Well, I suppose we should read some books here. There's a lot going on with the library and this and that, you know, and trying to figure out these things. Take a look at Feynman, Richard P. Feynman's physics a little bit more to give some hint on how he deals with the issues of even just getting to the next higher order of things in physics. So we're trying to figure out how do we get all the way from the little end of the telescope on down? Is like, I'm looking at it from the wrong end here, you know? What are we supposed to do? It's like, well, that's the only one that our mitts can handle, you know? It's like, well, what if you turn it around, you know? How is that going to look? It's like, that's the idea here. Okay. It's a bit late in the afternoon. I don't drink much coffee after 2 or 3 p.m. anymore, or I'll be awake very late, past bedtime, which is early these days. So let's take a look here. Lectures on physics. Richard P. Feynman, Feynman, Leighton, and Sands. Consulting a random page. Colorimetry, perceived color, talks about and shows a diagram of the sensory apparatus that converts the special optical character of visible light into, after redshift and blue shift and green and luminance and chrominance and hue, saturation, brightness, subtractive and additive colors, the primary, these things that visual light is special, optical and geometric, and it helps to reflect that this notions of diffraction and all the things to do with this relativity, special relativity, but really the acoustic model, the phonons before the photons, has that everybody is particle potentially at light speed, or potentially at the speed of sound, or potentially at not zero. Vis-a-vis that, according to the theories of relativity, it's just like there is no absolute motion, but things appear to move. Other eyes. Besides the bees, many other animals can see color. Fish, butterflies, birds, and reptiles can see color, but it is believed that most mammals cannot. Primates can. Birds certainly. So, when we talk about the light is usually just the luminance, and then the chrominance has that, it still has an input. Kind of like the differences of kinds of shades of green. Some people can see like 40 times as many people than us usual sorts of people with perfectly suitable and accurate color vision, who are not, say, colorblind or truly colorblind. And it's usually said to have more rods and cones in their eyes, or as with regards to that, or that their construction of like this model of the frog, he says there's the retinine, the electron micrograph of a rod cell, the cones and rods. So with regards to the ommatidia in the eye of a bee, the optimum size for ommatidium, that this reflection on vision gets into many eyes with that have focus are spherical or globular, the eyeballs. And there's much to be said because for this parallax and peripheral parallax and the optical and the actual effects of light, and not just orientation in a terrestrial setting with regards to the sky and the horizon and stuff like that. That is optics are real. Light is both geometric and optical. It is so. The nerve fibers of the horseshoe crab. The frog's eye. One can find 4 different kinds of optic nerve fibers in the sense that there are 4 different kinds of responses. A frog. Sustained edge detection. So in the signals we talk about the level triggering and edge triggering, and the fact, for example, that in modern integrated circuits that sometimes there's just billions and billions of billions of one of those, sort of a monoculture of edge or level triggering with regards to the capacitive devices, with regards to passive and active electronic devices and current effect and these kinds of things. We may briefly summarize what we have just learned this way. There are 3 pigments, presumably. There may be many different kinds of receptor cells containing the 3 pigments. Where in the tectum of the frog, the nerves come to the brain from the optic nerve and make connections in the various layers of the tectum. And these are with regards to the pigments are very, very particular and special substances produced by the body and not to be introduced into the body, like melatonin and stuff like that, with regards to spirits, tinctures, and stuff to do that replicate or replace or displace the function structurally and of pigments. These are very, very critical, not so particularly well understood substances of the usual higher organisms like mammalia and so on, and most gentle readers and fellow earthlings. Quantum behaviors is next chapter. So he goes from light, which is like, do you know quantum particles or waves and particles? Well, light is both optical and geometric. They're not necessarily the same thing, because light's not necessarily particles, although Feynman knows everything about electron physics, and so he's like, I know everything about electron physics, and that makes all light photons. But light is rays, and electrons are static current, really. We would like to take up as our next subject the problem of the behavior of relatively large pieces of matter. Their mechanical and thermal properties, for instance. In discussing these, we will find that the classical or Otto theory fails almost immediately because matter is really made up of atomic-sized particles in the theory. And so we've had a lot of talks here before, and so there's at least two different perspectives with regards to watching this video and or listening to this talk, this recording. And one is that I have sat through about 100 hours of these recordings, and then after like 30 or 40,000 written essays, after reading about 10 or 15,000 books in years of study in this manner, but at least I've sat through all these videos with regards to a lot of these different concepts. First of all, establishing the comfort of our canon and our classical canon, and all the stuff that arrives at the entire standard linear curriculum, then the classical notions of the super standard and the superclassical, the paleoclassical that's also the superclassical, starting kind of from Heraclitus's dual monism, and that's also kind of the birth of philosophy, vis-a-vis the received tradition of the word, the number and the word, and this kind of stuff that all comes down since antiquity, since prehistory, and all that kind of stuff. Up to the modern day, where we have a great plane linear curriculum that gives us all the number line and the coordinate plane and all this stuff that's standard and defines the real and Israel. That then, with regards to this, the notion that matter is made of atoms, is that the atoms are a conceptual way to consider the uncuttable, the ultimately small, in the world of otherwise the infinitely divisible, the non-divisible, atomic, non-cuttable, non-divisible. And then with regards to our physical constants, that's defined by this electron physics, kind of as after the Millikan oil drop experiment. It was like, we have now figured out in Earth's gravity that this is the mass, thus the charge of an electron. And electrons are 1-to-1 to protons. Protons are 1-to-1 to atomic number. Atomic number is 1-to-1 to the elements. Elements are defined then by these orbital models, which are so perfectly relevant in all the stoichiometric, in the small compounds and numbers. And they fulfill a lot of these different roles with the covalent bonds, particularly first. It works out perfect. Bond angles, perfect, polarity and all these kinds of things. Getting up into the ionic bonds, getting up to the van der Waals, getting up to molecular chemistry and stuff, getting up where these different models of the atoms kind of like, it's kind of shrunk a little bit. It's no longer exactly our atomic model. It's above that, it's the molecular model again. Resonance theory. If these particles are waves, then if those are particles, then they're waves or resonances. So that the atom is not necessarily the grain of things. Also, beneath what we call the atom, which is defined by where these four forces or four quantities, but are conserved: mass, charge, neutron lifetime, and light speed. Have it that, and then now later I'm going to try and figure out how neutron lifetime and light speed help make for these three corners of the box, why light speed is the other constant. Relativity in a box. That would be a good one. So, but anyways. So the atom, what we call that the atom we call it the Democritan atom because it defines a kind of substance that is elementarily, without transmutating its atomic number, it is one of those that makes the surfaces and these substances of materials. It's matter, states of matter, right? So underneath that then is the subatomic. So electrons are considered outside of that. Protons are considered outside of that. Neutrons considered outside of that. They make up all that. And then with regards to the entire particle zoo, and then particularly the quarkian and the transplanckian, and that beneath this invisible regime, 25 orders of magnitude less in mass than us, is 25 orders of magnitude less than that, called superstrings, and that's supposedly sufficiently small because if the atomic isn't grainy enough to be smooth, then that's just the idea that this is the theory around atomic theory, including molecular theory. It's called molecular chemistry, or structural chemistry sometimes, and including models of flux and flow, vis-a-vis electron physics, the ultraviolet catastrophe. So for Rayleigh Jeans and Millikan, which then came in and ushered in Einstein, and for the photon and electron, and then carried out that from the old quantum physics or atomic physics, figuring out the stoichiometric ratios of things, to the modern quantum physics, which is like particle wave duality, is in effect, to including things like space contraction and like, well, either way we're going to figure out there's not an ether, it's going to be part of this theory. Then as regards to the modern, and it's like, it's been shown finally this greatest fundamental result is that in the middle of the atom, where it's the most tightly formed together, like the middle of the nucleus, it's asymptotic freedom in the middle, or the Slom and Weinberg, and I forget, after they invented the theory, I forget who got the Nobel Prize after them for making the experiment, but asymptotic freedom and the Quarkian and all that kind of stuff is a big deal. So particle wave duality first, Heisenberg uncertainty, Schrodinger's cat, all that kind of stuff, adding up to is like, this is the best we can guess. It's not foreseen otherwise by the mathematics we have yet, that there's a mathematics that is it, and the superclassical model of spin and what arrives at it is its own thing. That causality is still a thing, vis-a-vis that it's arbitrary, that theory can exist mentally, so that there's arbitrary freedom of information according to light speed being just free information, and that the applied information can be as of instantaneous. For example, if two people generate the same code book, march to different sides of the room, and then each crunch out their code book, they will both have the same code when they're done, for example. So that it all becomes one theory and this kind of thing. So where Feynman says, let's pick up where Feynman was telling us these things. In discussing these, we will find that the classical or older theory fails almost immediately because matter is really made up of atomic-sized particles in this theory. Still, we will deal only with the classical part because that is the only part that we can understand using the classical mechanics we've been learning. Quantum mechanics is the description of the behavior of matter in all its details, and in particular of the happenings on an atomic scale. So quantum mechanics is a discrete particle mechanics. It's particle mechanics. And then with regards to quantum amplitudes, and then with regards to those supposedly adding up for the wave function collapse, it's still a lot about this convention of being particles. It's got to be all particles. There's nothing but particles in the theory, this quantum theory. It has got to add up to be this field theory. Quantum particle theory is arrived at as like, we got to be a field theory, also a gauge theory, so that we have a metrizing norm everywhere. How, regardless of how contrived it may be, there is one. These are the kinds of things that make it so. The introduction to the subject of quantum mechanics. Quantum mechanics is the happenings on atomic scale. So it's the sum of histories, sum of potentials. And the path integral is kind of like the sum of histories, and then the sum of potentials is the extra classical part around that. There's one lucky break, however. Electrons behave just like light. These days, we might say, first of all, it's like instead of electrons moving, we talk about the current as electron holes moving. It's like, well, do electrons go around the circuit? It's like, well, no, but they kind of vibrate, and their waves, the holes they leave, or the crests and troughs of their waves go around. And then can we treat an electron just like a photon? It's like, well, no, because a photon is massless and chargeless, and an electron has mass and charge. And well, then why can you say you can treat them the same? It's like, well, from our bradyonic viewpoint, we can't really tell that an electron is going any slower than light, and from a tachyonic viewpoint, we can't really tell that things that aren't electrons are moving at all. Because the electron just kind of reflects this flux and the overall wider potential of the electrical field. which is kind of, it's a standing flux, and so the electromagnetic spectrum, electromagnetic frequency, applies to the transmission of radio waves as electrical, but with regards to the optical and light and nuclear rays, there are two different things, regardless of the fact then they both can be considered as with regards to wavelength and a frequency. The waves of electrons, a wave of electrons, or a radio wave, is never an electron by itself. Finally, there's like particle accelerators and stuff. It's like, well, we've made not just a ray of photons, we made a beam of electrons. It's like, well, that's quite a bit different. That's quite contrived. That's like the spallation of these particles. At the end of the day, then, though, we can kind of say, well, yeah, we've got frequency or wavelength, and from that we can talk about their energy. And so then it's just so many of these and so many of those. And then for the photoelectric effect and the effect of light and its energy on orbitals and their energy, like the photosynthetic receptors of plants, they're a great thing, or the photoreceptors of eyeballs for vision. We can talk about them in the same kind of way, to be kept in mind that energy is in its forms, and while energy is conserved because it's a conserved quantity, we also have these models where these other conserved quantities are all in effect, and they only transition as according to particular regimes or effects. It is the effect in physics that is like something's changing. Then the reversibility of that is going to vary, whether it stays in the same quantity or not. So let's see what it says. Historically, the electron was thought to behave like a particle, and then it was found that in many respects it behaved like a wave. So it really behaves like neither. Now we have given up. We say it is like neither. No, you can say it's like both. Yeah. And then he explains why the great strength of electron physics was like light and electrons work together. We call them all electromagnetic radiation. It's like, okay. But electrons are not optical or radio waves. The gradual accumulation of information about atomic and small-scale behavior during the first quarter of the century, which gives some indications about how small things do behave, produced an increasing confusion, which was finally resolved in 26 and 27 by Schrödinger, Heisenberg, and Born. They obtained a consistent definition of the behavior of matter on a small scale, in a single direction and for a small distance. Take up the main behaviors. Well, so that's interesting. You know, it's helping to kind of describe what goes into the unlearning that happens because you start trying to reach these things about the kinetic and kinematic of these particle models of waves as kinetic models of action, usually just for geometric incident reflection, most familiar as equal and opposite rest, mass, or the laws of motion, and then into these notions like the sum of potentials and all possible paths and this kind of stuff, their wave behavior, the optical, and diffraction, and then saying that it's all one thing, all one kind of thing, isn't so much unlearning as having to bookkeep at least two different things in one set of books. It's like there's a book, and then that is another book, and then that is another book. All one book. Probability. Then he gets into why probability accurately models this, because you can say it's like, we don't know, but tends to go in one direction. So probabilistically, it's probably going that way. Probability is not certainty by any means. And prediction is not assurance. and neither is it certainty, and neither is it probabilistic. Wavelengths, half wavelengths, the ability to use these mathematics to figure out. I was like, well, how are these things related? It's like, well, frequency and wavelength, they're reciprocals. So half of the one is like one half the other or twice the other, kind of depending whether some of these relations are like in or out of that. Trying to figure out these doubling and halving things so we can work out these addition formula, because all we have to add things up here is abacus or our fingers. So it's got to be addition formula. The interference of electron waves. So he's establishing that waves have their constructive and destructive interference. The mathematics for relating these patterns is extremely simple. The mathematics is the same as that we had for the water waves. It is right where they these crests and troughs meet. That's one of the greatest thing about studying electricity is like it goes around a circuit. It's like, what does that mean? Well, it's kind of like if you have water and you pump it around a circuit, according to the compressible and incompressible fluids, it's got to go somewhere and it will follow itself around the circuit. Then the idea is, well, like pressure is just like voltage, and resistance is just like constriction. Then what it gets into is like, but the fluid model for these fluid models, the liquid model is like it's got the core effect and the most velocity is in the center, and the electrical model's got the exact opposite thing. So Feynman says, hey, look, these waves, because there's this wave model is ubiquitous ever since this talk in moment and motion, defining things in terms of waves is the fungible thing of models of change in open systems. These these mathematical models of waves just add up just like the fluid model. Leaves out that on the extremes or at the boundaries, it's the exact opposite, which is relevant then to establish that that's where kind of the superclassical part is. And it's similar for stuff like superconductivity. And what happens when otherwise these reciprocal quantities, like in the passive circuits, that resistance and voltage equals current, or potential and resistance in current. The one of the goes to zero and infinity. It's the same kind of problem we're talking about as 0 meters per second is infinity seconds per meter, and vice versa. Well, all right then. Electrons, an electron gun. So he's talking about stroboscope and electrons, a cathode ray tube, various apparatuses, which a result sending a particular amount of quantity to the detector. And we've talked a lot here about beyond the phenomenological, what kind of tools can we define that would be a detector, and in the physical apparatus. And then we've also talked about our mental apparatus, the mental phenomenology of an object sense, a word sense, a number sense, a time sense, and a sense of the continuum. So we can arrive at this 0, 1, and infinity, even though our arms to count our fingers that far will never stretch to infinity. At the same time, mentally, our minds can make one in a box. See, so that's just like a bit of random reading about the optical nature of light, and then the quantum particle behavior, the definition, the formalism, propagation, ladders, filters of waves, a 4-vector. Then Feynman's next great thing after vectors is a 4-vector. And so that's basically says, hey, everything that I have made so far goes in a line and a straight line. And if it doesn't, now it's a 4 vector and it's got both sides. Then in physics today, they call it the multipole moment because they're like, in higher dimensions, it goes 4 sides again. And here what we're doing is we're making for Zeno's swaths path integral that in a box. And we've kind of discovered or invented the beginning of the definition of the opposite of Fourier-style analysis, which is to say we're going to take any function and approximate it by periodic functions and coefficients that add up to them. We're just going to take any function that's a straight line and then have whatever are all these different various possible ways, the extremes of all their shape and scale parameters that reduce to it to being 0. Now, of course, you can do this same thing for this Fourier coefficients to make a line that's 0. It's just 0. Now, and then one of the issues with defining this kind of analysis is sometimes it's said, well, you can't have constant coefficients of this kind of thing. It doesn't make sense. But the 0 is always sticking out as a trivial case because although it's the additive identity, it's a multiplicative annihilator. And so when we look at this this series, like the Fourier series, and we want to add stuff up to things, and it's part and parcel of all differential analysis. Similarly, this hat-style analysis is like, well, first you take the quadrant that's infinite and you shrink it to a box. So any functions in that, it has the same kind of graph as it does in the box. And then have them flip that over, and then it's like, well, then imagine that if you just went at a uniform rate all the way out to infinity, that then basically the hyperbola would become the opposite diagonal of the quadrant, connecting 0, infinity, and infinity, 0. Or in the box, just the opposite diagonal. It's kind of simple to say that. Then what we're talking about is kind of like a periodic function adding up to that being 0. That's the hat-style analysis, this inverse Fourier analysis. And so there's much more about that is in the descriptive differential dynamics bit. And then as with regards to here, that it's just kind of framing that if the last talk was more about Zeno's swath and just kind of establishing the goals and the precepts of modeling these multiple dimensions and relations of length and distance and to common quantities while keeping track of them, then this talk is mostly or pretty much about the idea of what analytical expressions make for that. Any one of those is one of these. Well, all right then. I shall so hope you enjoyed this talk today. What I shall so hope to do is to digest this, and then it would require quite a bit of machinery in the surrounds of the foundations of mathematics to arrive at these things being close to the center of things, central and primary. This in this sense of this continuum, this non-standard analysis, and with these laws of large numbers, various, and this and that. But then at the same time, this sort of hat-style analysis can also be built just completely standardly. As regards to figuring out its justification, this justification can be a lot simpler with a little bit of deductive analysis. But it should so surely offer an inductive justification as well. There are some constructive formalists that is like, I as long as I can just count it on my fingers, I got an arm 1,000,000 miles long. It's like, okay. Good day. Good luck. Stay cool. Don't light forest fires. or only you can prevent forest fires. So long.